Thank you, Katharina. Hello, I'm Manuel and I'm a roboticist. And Oliver already told you that we do intelligence research with different species. And Katharina showed you that mice can solve lockboxes. Now, as a roboticist, my species are robots. But not only, I also do research with cockatoos. And the core idea here is that by learning how cockatoos can solve difficult problems, maybe we can build better robots. And by using robots as models, maybe we can also better understand animal intelligence. And now let's start by talking about cockatoos. So what you see here are Goffin cockatoos at the lab of our collaborators in Vienna. And these are really curious animals that are known to do smart things like using and making tools. And now our collaborators in Vienna and Alex Kachelnik, who just talked to you, asked themselves, can these birds also solve lockboxes? So what the biologists set out to do is that they built another lockbox. And so these birds, the Goffin cockatoos, are crazy about cashews, and there is a cashew behind this plexiglass door, and they really want to get that. But to get that, they first need to, of course, open the door, but this is blocked by this bar. This bar can only be pushed to the side if you first remove this metal disc here, but this can only be removed when you first pull out this metal part here, which is in turn blocked by this metal screw, but that can only be turned if first you pull out that pin. So this is a really complicated problem. Now let's see if Goffin cockatoos can solve that. And so what you see here is, yeah, it's possible. They can do it, of course, otherwise I wouldn't show it, I guess. And I think this is pretty impressive. But it's also interesting research-wise, because also in the introduction, Oliver mentioned that intelligence happens at the interaction of different processes. And the solution here, this behavior, definitely requires many different skills to interact. So the bird needs to detect the lockbox, it needs to understand its state, it needs to have a good strategy that tells it what part of the lockbox to work on, it needs mechanical skills to actually open the individual parts, and of course it needs learning capabilities to actually learn that behavior. And yeah, so to sum up, there are many different components and processes that interact to get the bird to this point. But how does it actually get there? And to find this out, together with the biologists, we wanted to do a new experiment. And this experiment is a reduced version of the previous lockbox. So what you see here is just the door and this bar. And first, the bird learned to solve this reduced lockbox. And then what happened was that we additionally introduced the wheel and then wanted to see how does the behavior of the birds change when the experiment changes in this way. So this is a bird that sees this new version of the lockbox for the first time. And what you see is that it repeatedly tries to open the bar and the door, but it doesn't really touch the wheel. And this goes on for a while. And so, to be honest, maybe it doesn't look that smart at the moment. But the first thing that this can highlight for us is that lockboxes are a really nice experimental paradigm, because in a way you can watch the animal think about the problem by seeing what it does. And then also what it does is actually, I mean, it makes sense because it wants to get the cashew. Whatever keeps it from getting to the cashew is probably close to it. So working close to the cashew on the lockbox makes sense. But maybe it indicates that the birds do not have a highly dedicated physical reasoning capability, because a human would probably very quickly find out that the disk now blocks the bar and would start working on the disk. Yet, if you look at the same bird, after it had a little bit more experience with the lockbox, this bird very quickly became a professional lockbox solver. And yeah, so this is now way, way quicker. And what's interesting here is that this behavior builds on the innate capabilities that these birds have, because in nature what they have to do is they need to pull seeds from cracks, they need to crack nuts, they need to sometimes break things to get to their food. And in a way the lockbox problem is a problem like that. But what's impressive is that adaptation allows them to go beyond that and to use these skills in this new setting. And we think that this is, we can call this intelligence. Okay, but how do they actually get to that point? What changes as they learn to solve the lockbox? First of all, what we can see, analyzing a lot of data, is that the birds improve in their trajectory. And what we see is that while the first solution takes a lot of time, like between 30 minutes and 1.5 hours, then the second and third solutions and later solutions are, there's a sudden drop in the time they need to solve the lockbox, and then it's more on the order of 30 seconds. And so this is interesting because they learn very quickly, but then also there is ongoing learning. So even after a lot of sessions, they still become better. And this indicates for us that maybe there are two different learning processes going on at the same time. And then what we also can see is that different things change as the birds learn to solve the lockbox. They become more engaged with the puzzle, which means that they become more motivated in a way. As they learn to solve the lockbox, they want to work on it some more. They learn better strategies, so they learn what parts of the lockbox to interact with to solve it. And also they learn the mechanical skills they need to open the individual parts. And after a while, they manage to do that with less actions and less contacts. And interestingly, these three things are interdependent, because you need to be engaged with the puzzle to learn a strategy and skills. You need a good strategy to learn to solve the lockbox, and then with that comes engagement. And also you need a strategy to learn the mechanical skills, because if you don't touch the right parts, of course you cannot learn to mechanically resolve your problems. And the other way around, you need to be able to mechanically remove the disk in order to learn a good strategy. So I think this interdependence is interesting. So much for the birds for now. That's not the only thing that we did. What we also did was that we built an upscaled, robotized version of the lockbox. And so before this video here, the robot was able to explore the lockbox, and what you see here is a playback of its solution. And in the exhibition hall, you can see a new version of this experiment. Now, building these robots, or these systems, is really educational to us as roboticists, because first of all, it makes you understand how difficult that problem actually is. It really makes you appreciate biological intelligence. And also, it tells you what parts are involved in the solution to this problem, because this robot needs to move, so you need control theory. This robot needs to see the lockbox, so you need methods from computer vision. And also, this robot needs to learn, so you need methods from machine learning. And all of these things, again, need to interact. But why is this actually interesting to us as roboticists? Well, I think to answer that question, let's talk about what we want robots to do. A dream that I have, and maybe a few of you share, is that I would like to have a robot that can clean up my kitchen and cook for me. And are we there? No, we're not there yet, of course. So where are we? Well, right now we have robots in factories. And this works because factories are predictable environments, and they are known environments, and the people who engineer behavior for these robots can rely on precise models of this environment. But a kitchen is not like that. Every kitchen is different, and we cannot really give robots, a model of your kitchen when we send it to you. Ideally, the robot needs to build this model itself. And as it turns out, that may involve solving a lockbox problem. So think about your dishwasher. If, for example, you want to put a dishwasher cleaning tab into a dishwasher, what you need to do is you need to open the door, and after you open the door, you need to open the tab compartment. Or even worse, let's say you want to put in dishwasher salt. Then you need to open the door, then pull out the tray, and only then can you open the compartment for the salt. And if a robot needs to be able to figure this out by itself, this is in a way solving a lockbox problem. And so using a dishwasher, an everyday problem really, is very similar to solving a lockbox, which is the task that we use to investigate intelligence. But so we don't really do kitchen robotics, to be honest. We are interested in understanding intelligence in birds and robots. And this was just an example to motivate it. But I hope that this convinces you that jointly researching mechanical problem solving in robotics and in biology makes sense. And the idea here, I want to reiterate on that, is to build better robots. It probably makes sense to understand how intelligent animals solve similar problems. And also using robots to understand intelligent animals is sensible because, first of all, by using robots, we can actually look into the animal that we're researching because we have a full understanding of the internal workings of a robot, and we don't really have that for animals. And also, we can arbitrarily change robots and then see how changes to robots lead to changes in behavior, and we can also not arbitrarily do that with animals. And this is one of the core ideas in SCIoI, that we need to jointly understand intelligence from an artificial and from a biological perspective. Thank you.